Okay. Good morning to all of you, and I welcome you all to this session of conduction and convection heat transfer. Last class we were discussing about the steady one-dimensional heat conduction, and we discussed various problems related to plane wall with boundary conditions given as temperatures at the two faces, and how to take care of the convection heat transfer when the fluid temperature at the two sides are specified. And we discussed the analogous electrical circuit specifying the conduction and convection resistances. Today we will discuss a simple classical problem of conduction, one-dimensional steady-state conduction heat transfer with heat generation. It is a simple but classical problem. The problem description is like this. Again a plane wall whose width is L, while the dimensions in other directions, that means in this direction perpendicular to the plane of the board, and this height are much higher than this dimension, so that we can consider the temperature is a function of one coordinate system x, and the problem is specified like this. There is a heat generation or thermal energy generation within this wall, this solid material. In a way, the volumetric heat generation Q, G is constant. That means with uniform rate of thermal energy generation per unit volume. Point to point, the thermal energy generation per unit volume is constant. That means the total thermal energy generated can be expressed as Qg times the total volume. Now, the boundary conditions are prescribed like that. The walls are kept at, both the walls, at a temperature Tw. This is temperature Tw. Now, we are interested in finding out the temperature distribution and the heat flux. Now, here you see both the sides are at the same temperature Tw. So, how the heat transfer will take place? Because of the, physically understand the problem, because of the thermal energy generation within the solid, the temperature will go high. So, therefore, the heat will flow to both the surfaces. Tw is relatively small, and we expect that because of the generation of thermal energy, temperature will be much higher than Tw. It is a practical problem, cooling a wall, cooling a plate, so that Tw is kept small. So, therefore, heat will automatically flow when the temperature will rise because of the energy generation. So, it is not necessary that one surface has to be at higher temperature, another surface. For example, without any generation of thermal energy, both surfaces at same temperature, there is no heat flow, until and unless you initiate the problem by making temperature within the solid higher than that. This is being done by the heat generation. Now, this problem, the starting point is this. We know in a plane area, and another thing is this problem, that thermal conductivity K is constant. Thermal conductivity K is constant. Now, if we start with our basic equation of one-dimensional heat conduction with heat generation, this is the starting point that we discussed earlier, that this is the starting point, because this is our one-dimensional heat conduction with heat generation. Last class I have seen that you one-dimensional, if you again write this, you will get that ddx of K dt dx, del t del x plus del y, this is del x del del y of k del t del y plus del del z of k del t del z plus qg is 0, because the temporal derivative of temperature with time, that is 0 for steady state. So, for one dimensional these quantities will be 0. Again I am doing this. There is only one term in the spatial derivatives, and for constant k this now del del becomes ordinary differential equation, ordinary differential nomenclature, k dt dx plus qg is 0, and when thermal conductivity is constant we come to this equation. Now we have to solve this equation. Now the rest part is the solution of this equation, that constant thermal conductivity and with constant volumetric heat generation rate, that is qg, to solve this equation, which is extremely simple. You have done at school level. If you write this d square t in this fashion, dx square is minus qg by k. By the problem both qg and k are constant. So therefore, if we integrate twice we get the solution like this, t is equal to minus a constant, no, this is qg by k is constant, treating qg by k constant, 2x square plus c1x plus c2. c1, c2 are two constants. You integrate first, you get qgx by k, then x square by 2 plus c1x plus c2. Now, to know the boundary conditions c1 and c2, to know the constant c1 and c2, we have to know the boundary conditions. What are the boundary conditions? Now, when you specify the boundary condition, you have to specify the coordinate axis. Now, this type of problem, usually for convenience, we take the coordinate at the middle. Why? Because this is a symmetric problem. Problem is symmetric. The geometry and the boundary condition is such that both sides it is TW. That means if we have a mid plane, about the mid plane the problem is symmetric. Q is uniform throughout, which means it is symmetric about the mid plane. The boundary conditions TW at the two faces are same. That means the problem is symmetric about this mid plane. So therefore, this mid plane or the mid axis, as you see in this view, is taken at x is equal to 0. So that left face is at x is equal to minus L by 2 and right face x is equal to plus L by 2. But it does not matter, you can take x0 here, so that this will be x is equal to L. Now, if you take the axis at the middle because of the symmetry of the problem, then boundary conditions is that at x is equal to L by 2, t is equal to TW. At the same time, at x is equal to minus L by 2, t is equal to TW. Now, if we use these two boundary conditions, C1 will be 0. Mathematically, C1 will be 0. But this C1 0 is obvious without writing the boundary conditions. This is because the problem is symmetric, so that there cannot be any term containing x. There cannot be any term containing x. Another way you can look at that, when this is a symmetrical problem, that means temperature distribution also will be symmetric about this axis. That means this axis will correspond to either a maximum or minimum temperature, which means the derivative is 0, which is sometimes known as symmetric boundary condition. At x is equal to 0, dt dx 0. This we call as symmetric boundary condition or symmetry boundary condition. Symmetry boundary conditions. This we tell as symmetry boundary condition. That means if x is equal to 0 is the line of symmetry, then there the variable shows for a minimum. If you straight put these boundary conditions here, you will find out that C1 is 0. C1 cannot exist because the temperature function, if it is symmetric, it cannot have a term x which will assume a plus value in the right side of the axis and the minus value on the left side of the axis. These are extremely simple things, but from many angles that can be considered, so that immediately we make C1 0. So C2 will be simply, what is C2? C2 will be simply TW, C2 will be TW plus QG by L by 2. If I use any one of these, that will give the same result. That means 8K L square. This is C2. Then the final temperature distribution will be T. Now, if we put C2 here, minus TW is equal to QG by 8K L square minus QG by 2K X square, which we can write in this fashion: QG by 8K, taking this common, into L square minus 4x square. So this is precisely the temperature distribution within the rod. When we have neglected C1, means we have taken the symmetry boundary condition dt dx 0 at x is equal to 0. If you see that, you will see dt dx is 0 when x will be 0. And the second derivative is negative, which means the temperature attains its maximum value because of the internal thermal energy generation at the axis. So if we express this at T0, T0 is the maximum, T is equal to T0 when x is equal to 0. That is the maximum temperature. Then we can write T0 minus TW is QG by 8K L square. So I can find out the maximum temperature which occurs at the center or the mid axis like this, and we can express the temperature distribution in a normalized fashion like this: T minus TW divided by T0 minus TW is equal to Q L square minus 4x square divided by L square, 1 minus 4x square by L square. This is one way of expressing this in a normalized fashion. Or if you add minus 1 on both the sides, then you can write this thing as T0 minus T divided by T0 minus TW. Minus 1 I am adding and changing the sign is equal to 4x square by L square, because this shows a parabolic variation with the maximum value at the center. So this can be represented in this figure by some T0 TW scale here, TW scale here, like this. This is my T0 value in the same scale. So this will be the temperature variation. This will be the temperature variation. That means the equation of this is T0 minus T, T0 minus T divided by T0 minus TW is equal to 4x square by L square. That means x is equal to 0. It will assume a value of T0. Sorry, it will be something wrong. T0 minus T at yes x is equal to 0, the value is t is equal to tw and x is equal to L by 2. That means t is equal to t sub 0, okay, t0 is t, is all right. I think it is all right. X is equal to 0, t is equal to t0 and x is equal to L by 2, t is equal to tw. It is perfectly all right. That means this is a parabolic distribution. Now we are interested with the heat flux from the surface. What are the heat losses from the surface? We have to know this. Accordingly, we can design the coolant. We can find out what coolant we will use, what type of heat transfer coefficients I have to provide, whether we will make a natural convection or forced convection. So therefore, this parameter is very important. Q at x is equal to L by 2 and Q at x is equal to minus L by 2. These two things are required. Now let us write that Q is equal to minus Ka dt dx. That is by Fourier law of heat conduction. So at x is equal to L by 2, it will be dt dx at x is equal to L by 2, and as minus L by 2, it is dt dx as x is equal to minus L by 2. So dt dx at x is equal to L by 2 is what? That you can find out from this dt dx at x is equal to L by 2 is T0 minus Tw from this equation. Dt dx is T0 minus Tw. Now this is 8x by L square, and at x is equal to L by 2, it is 4, that is 8x by L square, and if x is equal to L by 2, it is minus 4 by 8 L by 2, 4 by L. This is okay. T minus Tw divided by T0 minus Tw is 1 minus 4x square by L square. So therefore dt dx will be T0 minus Tw minus of 8x by L square, 8 into L by 2, that means 4 by L. This is okay. That means minus T0 minus Tw into 4 by L. Then what is dt dx? It is okay. What is dt dx at x is equal to minus L by 2? What is dt dx at x is equal to minus L by 2? Try to find out the same thing but with a positive sign. That means T0 minus Tw divided by 4 by L. Okay, clear? 4 by L. Now here Qx, Q at x is equal to L by 2 is minus Ka dt dx. That means it is positive. That means Ka T0 minus Tw into L by 4. Okay, and Q at x is equal to minus L by 2 is there any mistake? Oh, sorry. It will be x is equal to minus L by 2 is minus Ka T0 minus Tw into 4 by L. Okay. So therefore, we can find out the rate of heat transfer in terms of T0 and Tw by this. Now here the positive sign indicates that the heat is transferred in the positive direction of the x. This is Q, and here heat is transferred in the negative direction of x. So therefore, we can find out the heat transfer from the two surfaces by finding out this dt dx. Okay? Any problem? All right. So you can also check by energy balance that if you make the summation of these two, that is the scalar sum of these two heat transfer, that will ultimately equal to the heat generation. If we write this Tw in terms of this is your task, that Tw in terms of T0, T0 minus Tw is Qg8K by L square. You just substitute it and you find out the value of that. I am not doing. Qx is equal to L by 2. That means it is a very good check that Q at x is equal to minus L by 2. Now if you just substitute T0 minus Tw in terms of the heat generation, Qg by 8K L square, that means there will be a, and this Kk will cancel, and this will ultimately comes like ALQ. If you do it, this will come like that. That means if you now eliminate this T0 minus Tw, that means a check that the total heat loss from two surfaces, the sign is the direction. But if I take the scalar sum of these two, that means energy balance tells that heat loss from both the surfaces equals to the total internal energy generation, because we have satisfied the same conservation in a differential form, point to point. That means the gross has to be balanced. There is no doubt of it. It is a stupid phenomena that why are you doing, sir? But still, for satisfaction, we have used the differential equation for point to point. Why not you make a gross balance as a whole, that the heat which is flowing out from the two surfaces equals the energy generation, which means the steady state concept persists. That means there is no energy accumulation within the system. So this is a very simple example, classical example of heat generation. Now I will solve some important and interesting problems in the class. But before that, I will discuss one thing which has not been told very explicitly in your class already by this time, though I mentioned it at the beginning, but I will tell that. Let me rub the board. The problem is like this. Before going to the problem, I will discuss one thing that I told, that one-dimensional steady state heat transfer truly happens when the area normal to the heat flux is not varying in the direction of heat flow. But sometimes by some approximation we use one-dimensional analysis for such a area varying substance. Let us consider a tapered rod like this, where the boundary condition is such that this faces is kept at some temperature T1, this phase is T2 and T1 is greater than T2. Sometimes the problem is specified by insulating the lateral surfaces. But what is done that here, if x is in this direction, or you can take at the middle axis, same thing, x, then we tell that t is a function of x, and sometimes this problem as a one-dimensional problem. What is the meaning of that? When the area varies like this in the direction of heat flow, in fact, t becomes also a function of y. But if the area variation is not much, or the boundary conditions are such, the lateral surface and the end surface says, we can neglect the variation in the y direction, that means cross-sectional variation, and we can consider almost a uniform temperature the way we have considered for a plane wall, and that is only a function of x, where the heat is flowing by virtue of the main potential difference T1 and T2. Or we prescribe the problem this way, that though truly it is a two-dimensional heat conduction, T is also a function of y. Truly T is a function of x and y, maybe a weak function of y, but it is a function of both x and y. We consider an area average temperature, and that area average temperature as a function of x. Whatever may be, in both the cases, how do we perceive? But it is a function of x, whether it is an area average temperature or a constant temperature, neglecting its variation. But we cannot neglect the variation of area. So therefore, we cannot write the equation d square t dx square 0, because we know the equation is in this form. The general equation is in this form, k a dt dx plus qg into a is 0. This is the basic equation. Where from does it come? Your general energy, general heat conduction equation is not there, A coming into this, because there we have considered plane area. Now here, if you derive this, I think it will be always better. I suggest you that for steady one-dimensional heat conduction, better we always derive the basic equation relating the temperature variation by taking a small element, the way we derive the heat conduction equation in 3 dimensions. Taking a small element at a distance x, where the area is Ax. Now Ax, why I am telling that this A is a function of x, Ax. Now I write Ax. I derive this equation Ax, which is a function of x. It is changing. The heat flux is Qx, and we consider the element of thickness, that means this one, delta x. So therefore, the heat which is going out, Q at x plus delta x. Now I write by Fourier heat conduction equation at that section Ax at a distance x, Qx is minus k Ax dt dx. This T is a temperature which is cross-sectionally uniform or a cross-sectionally average temperature. We can write by the expansion in Taylor series, Qx plus dx is Qx, that is minus Kax dt dx, plus this quantity Qx ddx of minus change Ka dt dx over a distance delta x. But this is an infinite series. We have to take higher order term, HOT, I am writing higher order term in delta x. That means delta x square by 2, delta x cube by 3. You know the Taylor series. and since delta x is extremely small in the limit tends to 0, so these terms are being neglected. So therefore, from the energy balance, if we consider at that section Qg is the heat generation, then definitely I can write Qx plus del x, what is coming out from that small element is nothing but Qx plus the amount of energy that is generated, that is Qg into Ax into delta x. This is my, so therefore derivation of general heat conduction equation, or for one dimensional simple heat conduction equation for your purpose, the procedure is same. To make an element, take the energy balance by describing the heat flux by Fourier heat conduction equation. And in energy balance, we have not considered the change in internal energy because it is at steady state. That means energy coming in and energy going out must balance with the energy generated, so that no energy may be accumulated or depleted within the element. So if you write this and if you make this, then you get this equation. You write this Qx plus dx this side, so this cancels, so this plus this is in the left side, this in the this cancels, so this becomes equal to Qg Ax delta x. So ultimately by substituting these two you get this. So that means our starting point, even if the area varies along with the thermal conductivity, is this, which in a very special case, I can rub this now, in a very special case becomes that if Qg is 0, that means there is no heat generation. If Qg is 0, then this becomes ddx of Kax dt dx. That means we see that without heat generation this quantity is 0. And if we take K constant, thermal conductivity does not vary, then we come to this conclusion, ddx of Ax dt dx 0. That means still we cannot say that dt dx is constant, temperature is linear, because we are considering the variation of area. But if the area variation is not there, that means a plane wall, then it comes out and d square T dx square 0, then only we get a linear temperature variations. There will be problems where a area variation will be there. That means if the area varies, how do you tackle the one dimensional heat conduction equation? Clear? This can be also appreciated that if we consider the variation with y, how I am telling that mean temperature comes into consideration, let me do this way, that you can be satisfied this also, that this is, we have already considered a mean temperature, where from this comes. Let us consider a section at x. Now if we consider that t is a function of x and y, this is an integrated form. Now if I have to find out the value of Qx, that means at this section, what is the value of Qx? Then what I do, let me consider this is h, the height at that section, and we consider a unit width of the rod perpendicular to the board. Now since t is a varying with y, so dt dx will change from y to y. This is not same along the cross section. We allow this variation. Then what we do, we take a element dy in this height, whose area is dy times this width. let this width be L, width perpendicular to the board be L. So, if we tell this the heat flux through this elemental area dy into L, not H into L, that is Ax, not that, then we can write del Qx is equal to what? Minus K L dy into del T del X at that particular y, because T is a function of y also. So, del T del X will vary from point to point. I take an element dy, so that I can integrate. That means Qx is nothing but the integration of del Qx. Now, to integrate this, let me take an axis, a symmetry axis is x here, so that plus h by 2 to minus h by 2. What we do? We do this one, minus integration of K L dy del T del X minus h by 2 to plus h by 2. Clear? L is the width in this direction. Now, if we consider K not to be a function of y, only T is a function of y. K may be a function of x, may not be a function of x. Rather, I take K out minus K L. Then what I write? Minus h by 2 to plus h by 2 del T del X dy. Now, if T is a continuous function of both x and y, which is supposed to be there in a physical system without any discontinuity, then I can take this integration out of this, the differentiation out of this integration. That means Qx is equal to minus KL del x of integration of T, because this is del x of T, T dy minus h by 2 to plus h by 2. That means I can take the differentiation out of the integration, and this is nothing but a mean temperature. If I define now a mean temperature Tm at any cross section is a cross sectional average mean temperature, which I can define TL dy from minus h by 2 to plus h by 2 divided by h. So, therefore, if I define a mean temperature like this, then Qx becomes is equal to minus K L H into del T m del x. And in that case, when you have defined a mean temperature cross-sectionally average, then del x will not be there. That will be simply ordinary differential, and L into H is the AX, area at that section. That means when I represent the heat flux in a variable cross section as minus KAX dt dx, this we consider that T is either some cross sectionally average temperature which is a function of x only, or we discard the variation over the cross section. So, until and unless you appreciate this, it will be difficult to understand that variation of area how I will take care of. That means you have to start from this equation. If you start from the equation d square T dx square equals to 0, you are gone, because that is not the governing equation. That does not take care of the variation of area in the direction of heat flow. Truly speaking, this is not a two-dimensional heat transfer problem. Here T is a function of both x and y. If the area variation is not great or not large and the boundary conditions are such, then only we can do that. Okay. So, after this now I will solve some interesting problems. Now the first problem which I will solve is like this. So now please, this is very important. Until and unless we solve problems, we will not be capable to develop our ability to analyze problems. Now this problem tells that a steady state heat transfer in a tapered rod like this. There are some problems which I will not tell you the language or not show you the language. You can write in your own language. This problem is described like this. But for a big problem, I will show you the language. Now this is a tapered rod, the same thing which I did now. It is a straightforward application of a symmetrical tapered rod, where this x is this direction, this is x, where it is given the Q, the total Q which is coming here is 6000 watt. 6000 watt. Q is equal to 6000 watt. Now a steady state heat transfer. Now AX, here they are writing like that, A as a function of x. That means that any cross-sectional area, this is AX, which is, this is AX, which is given by 1 minus x, where x is in meter and this is in meter square. How? We consider a unit depth of the tapered rod, that means depth L. If you consider L, that means this direction dimension L, then L is equal to 1 meter. So x in meter, so therefore this into 1, so this is the expression. The temperature distribution as measured experimentally is 300 into 1 minus 2x minus x cube. It is given in Kelvin. Kelvin, big K. X in meter and this is Kelvin, means 300, this constant is a dimensional constant. This will be Kelvin per meter. Oh no, Kelvin per meter cube, because 1 minus 2x minus 3x square. This is given Tx. Now we have to find out, what we have to find out? We have to find out the K, expression for K. This is the simplest problem to start with. That means this is a steady state equation. So which equation we will write? We will write d dx of K A x. A is a function of x into dt dx is equal to 0. That means K Ax dt dx is 0. But we are not interested in the temperature distribution. Temperature distribution is known. So we are not interested in this. So what we have to do to find out the K? We know the heat flux, steady state, heat, total heat transfer, not heat flux. I am sorry, here the heat flux will not be constant because it will be times the area. The total heat transfer will be constant. That means Qx, we have to use this equation, is minus K Ax dt dx. We have to use this equation, Qx, because Qx is given. Qx is given. So we write this equation and find the value of K. So what we will do? We will write the values that given 6000 watt. That means 6000 is equal to minus K into A. A is what? 1 minus x into dt dx. That means 300 into 2 minus 3x square. 300 into 2 minus 3x square. dt dx minus kx minus 2 because this is minus 2 minus 3x minus 2x, correct, sorry, that minus 2 minus 3x. So this is the simplest problem, and finally k comes out to be 20 by, because 6320 by 1 minus x into 2 plus 3x square. This is to start with, just warm up match like that. So warming up with this problem, that if a variable area is there, how can I take care of this area variation? That means our starting point, we have to remember that without thermal energy generation, this is the equation, not d square t dx square 0. Taking care of everything. If thermal conductivity constant, this comes here. So d dx of ax dt dx 0. But here temperature distribution is given already. I have to find out k, and I have to see what is given in the problem, total heat transfer, heat conduction, which is be same for all sections under steady state without heat generation. That means for any section, Qx is minus Kx dt dx, where Qx is 6000, flowing through all sections. This clear? This is as simple as anything. Very primary school level things are like that.